In the example we just looked at, we integrated with respect to x. All of our integrals were dx with respect to x. And what that meant was that we were slicing vertically. So we were finding all of these vertical rectangles, and we were repeatedly doing that, adding them all together, and that led to an integration. But it is possible to slice horizontally instead, and that means that we would be integrating with respect to y. So here I've got it drawn out where I've got two functions, an f of y and a g of y. So again, we're integrating with respect to y, so instead of f of x and g of x, we've got it in terms of y. So we've got these two functions that sort of run vertically left to right as opposed to horizontally up and down in the previous example. And so you can find the area between those two curves by sort of taking the whole axes and flipping them around and integrating with respect to y instead. What it does is it means instead of your interval going from a to b, left to right, your interval is going to go from c to d, bottom to top. So we have this new definition here of how to integrate, or how to find the area between two curves when you're slicing horizontally or with respect to the y-axis. And you can see that it's essentially the exact same formula, we just have a couple of different letters plugged in because we've switched the axes. So our interval goes from c to d, bottom to top, and then our functions are in terms of y, f of y minus g of y with respect to y. Now, in the previous example, f was always on top and g was always on the bottom. When we do this with respect to y, f is always going to be on the right and g is always going to be on the left. Okay, so it's bigger, f of y is bigger, meaning it's on the right. Up here, f of x is bigger, meaning that it's on the top. So let's take a look at an example where we do find the area between two curves with respect to y. Alright, so it'll specifically say in your homework on some of these problems to integrate with respect to y. Other times, it'll say it's your choice. You can integrate with respect to y or x. And you just have to judge based on the graph that you draw which one seems to be more appropriate. Okay, so let's say that we have two curves given. So we've got y equals the square root of x over 2 plus 1. And we've got another curve, y equals the square root of 1 minus x. And so what we want to do is we want to find the area between these two curves. Alright, so one of the things that we need to do is graph these. Sometimes use my little ruler here to make nice axes. I'm definitely not trying to advertise this company. I apologize for that. Okay, so you do need to figure out how to graph this stuff using some algebra, plotting points, whatever it is that you need to do. But if you need to do it quickly, or you need some assistance because you can't remember what something looks like, you can use your graphing calculator. Oops. So I don't know how to really make this clear. The bottom line is use your graphing calculator to help you, but when it comes to mastering this and being ready for an exam, you need to remove yourself from the graphing calculator so you can't get too dependent on it. Alright, so here we have the graph of the two curves. And so the more precise your graph, the better. Mine's going to be kind of sloppy for right now. But it looks something like this, and we want to find the area between the two curves. And so the hint on this one that we're going to integrate with respect to y is that instead of one function sort of being on top of the other, it actually looks like one function is to the right of the other. And so that's when we switch that axis of integration. All right, so whenever we integrate with respect to y, one of the things that we have to do is we have to rewrite our functions in terms of y. Okay, so I can't have y equals something with an x in it. Instead, I need to have x equals something with a y in it. So let's do that for each of our given functions. So this first function, again, I need to get x by itself instead of y. So if I square both sides and then subtract 1, I have one more step to isolate x, and that is to multiply both sides by 2. So this is one of my functions. And it is important to know whether that's the function that's on the left or the function that's on the right. And so this one is actually the function that's on the left. Okay, and so you can, when you're drawing your graph, you'll be able to figure out which one's which by plotting some points. All right, I need the other one in terms of y as well. So I'm going to square both sides. And then I'm going to subtract 1. And then I'm going to multiply by -1. Okay. So a more common way of writing -y squared plus 1 would be 1 minus y squared. But it doesn't really matter. All right. So I've got my left function and I've got my right function. I actually also need to know, well, let me try that again. I was going to say I need to know what my a and b are, but it turns out that I need to know what my c and d are because I'm integrating the other way. So I need to know my lower and my upper limits. Okay, so I need to know how low does this go in terms of the area, and how high does it go. So typically we're finding left to right in terms of a and b, but because we're integrating with respect to y, we're going to go bottom to top in terms of c and d. Either way though, this value is going to be determined by the point of intersection between our two functions. So we do need to calculate that by hand. So we can do that quickly here. So I'm taking this 2 times y squared minus 1, and I distributed the 2, and then I'm setting it equal to 1 minus y squared. Okay. So if I add y squared, I'll get 3y squared. If I add 2, I'll get 3. So y squared equals 1, which means y equals plus or minus 1. Now only one of those values actually makes sense. If we look at our graph, everything's above the y-axis. So y equals positive 1 is the value that makes sense. Alright, so let's set up this integral. So I'm integrating from 0 on the bottom here, that's my lower limit of my interval, up to positive 1. And I need to take f of y minus g of y. And the bigger one has to come first, the greater valued function. The bigger is kind of a bad term, but whichever function is on the right in our region is the larger valued function. So in this case we have 1 minus y squared And we're going to subtract from that 2y squared minus 2. Again, I went ahead and distributed that 2 in my left function, and we're integrating with respect to y. So let's combine some like terms. I'm going to start off by distributing a negative. So I have 1 minus y squared minus 2y squared plus 2. And if we combine some like terms, we'll have negative 3y squared plus 3. Alright, so let's use our fundamental theorem of calculus. We'll find the antiderivative of this function, and we'll evaluate it on the interval from 0 to 1. So great time to pause and try some of this on your own, and then come back and check your work. We're back to check the answer. If we take the antiderivative of the first term, we'll actually end up with negative y cubed. And if we take the antiderivative of the second term, we'll get 3y. If we plug 1 into that function, we're going to get 2. And if we plug 0 into that function, we're going to get 0. So 2 is our final result. So just to review, you'll always want to look at the setup of the functions based on the graph. Is one on top of the other, or are they left to right? And that will tell you which axis you're integrating with respect to. And if it turns out that you're integrating with respect to y, then everything sort of has to be changed around. Your equations need to be rewritten so that they're solved for the other variable. And in terms of your interval, you need to go up and down rather than left to right. Other than that, though, the basic idea of the formulas of integration are the same. We're subtracting the two functions, and then we're evaluating it over the given interval. So that is the end of section 6.2 and our work for this week.